Our journey starts with something simple, a coil of wire. When current flows through it, it creates a magnetic field. This is Ampere's law. The current is the cause, and the magnetic field is the effect. The stronger the current, the stronger the field. And how do we know which end is north and which is south? Use your right hand. Curl your fingers in the direction of the current flowing through the coil, and your thumb will point to the North Pole. This is the right-hand rule. The end where the magnetic field lines exit is the North Pole. The end where they enter is the South Pole. Now, let's introduce a second identical coil. If I wind it in the same direction as the first and connect them in series, what happens? The current flows through both coils in the same sense. Their magnetic fields combine. We get a stronger, unified field. The North Poles are on the same side, the South Poles on the other. This is what we call additive polarity. The fields add together. Now, if we feed it alternating current, where the electricity constantly surges and collapses, the magnetic field does the same. It grows and collapses with the current. But watch what happens when I place these same two coils on a single iron core. Now I have a transformer. One coil will be my primary. I'll apply a voltage to it. The other coil is my secondary. It's just floating, waiting to do something. I apply an AC voltage to the primary. Current flows and a magnetic field builds up in the core. That changing magnetic field cuts through the secondary coil. And here's where Lenz's law comes in. Lenz's law says, the direction of an induced current is always such that it opposes the change that produced it. Mathematically, we write it as V equals minus N multiplied by d phi by dt. That little minus sign is the most important minus sign in electrical engineering. It tells us that the induced voltage is always in a direction to fight the change in magnetic flux. So what happens? When the magnetic field in the core is growing in one direction, the secondary coil tries to create a current that would produce a magnetic field in the opposite direction to slow down that growth. The result? The voltage induced in the secondary is the mirror image, 180 degrees out of phase with the voltage applied to the primary. To keep track of this relationship, engineers use the dot convention. We place a dot on the terminal of each winding that has the same instantaneous magnetic polarity. When the dotted terminal of the primary is positive, the dotted terminal of the secondary will also be positive, and vice versa. Now, remember when we placed the two identical coils, wound in the same direction, and connected them in series? We saw that their magnetic fields added, and we called that additive polarity. In that configuration, the dotted terminals were at opposite ends. If we reverse the winding direction of the secondary or swap its leads, then, by the same logic and explanation, the magnetic fields oppose each other. That's what we call subtractive polarity. You can easily test this at home with a small transformer and a multimeter. It's a simple experiment that proves these concepts. We'll just redraw these coils for simplicity and clarity. Based on our explanation, here's how you can determine the polarity of any transformer. First, apply a low voltage to one coil, that is, the primary. Then, connect one lead of the primary to one lead of the secondary. Now, measure the voltage across the remaining two leads. If the measured voltage is the difference, roughly the primary voltage minus the secondary voltage, then the connected leads are of the same polarity. This corresponds to subtractive polarity, that is, the dots are on the same end. If the measured voltage is the sum of the primary and secondary voltages, then the connected leads are of opposite polarity. This corresponds to additive polarity, the dots are at opposite ends. If you found this video helpful, don't forget to like and subscribe for more engineering and science content. Stay safe, and thanks for watching.